This video covers continuity. There's a fancy definition of continuity at the top because I want you to speak like mathematicians, but let's talk about a simplified definition of continuity. Let's see, continuity is basically the limit value equals the function value. That's how we know a function is continuous. Let's look at some examples where continuity fails. Let's go back to the other notes that we had for a moment. If we look at, all right, so it's obvious that the graph is not continuous at x equals -2. We have a y value of 2 and a y value of -1. Can't be continuous there. A more interesting case would happen at x equals 3. The limit when x approaches 3 is 0. But notice that f of 3 is actually equal to -1. So the limit exists, the function exists, but the limit value and the function value are not the same. So the function is not continuous. Now, if we look at the case of when x is 0, the limit as x approaches 0 is 1, and we also know that f of 0 equals 1. So look at this winner. 1 equals 1, so the limit and the function value are the same, and that's how we know a function is continuous. The limit value equals the function value. Exclamation mark. Let's jump into the notes that we did in class today. So graphically, we are determining if the function is continuous at the value of x. Now we have two cases. First, we have x equals -2. Oh, let's zoom out. So determine if the function is continuous at the value of x. We're doing x equals -2. Right, might as well go and circle it now. So x equals -2. We are circling for no reason. So when x approaches -2, the limit is, it seems like that's 2, 4, 6, 8, 9. The limit as x approaches -2 of f of x equals 9, and f of 2 also equals 9. Is the function continuous at x equals, that should be a -2, at -2? Yes. Yes, we would put continuous because the limit as x approaches -2 of f of x equals f of -2, and both of those things equal 9. That's how we know it's continuous. The limit equals the function value. Now, if we look at x equals 0, we can look when x approaches 0 from the left, the limit is 5. And when x approaches 0 from the right, the limit is 2. So in the case of x equals 0, we would say, let's be fancy, f of x is not continuous at x equals 0 because the limit does not exist. That's why it's not continuous. For the next example, we have a parabola where we have x equals, we're determining if the function is continuous at x equals -3. So let's see, the limit as x approaches -3 of f of x is equal to, so both the left limit and the right limit are -2, but then f of -3 itself is -1. So in this case, is the function continuous at x equals -3? The answer is no. We would say the limit as x approaches -3 of f of x is not equal to f of -3. This value was equal to -2, and -2 is not equal to -1. Let's not write down at x equals -1. Well, you know what? Let's be consistent. So the limit as x approaches -1 for f of x is equal to -1. f of -1 also equals -1. The limit value and the function value are the same. So according to our definition, the function is continuous at x equals -1. That's it. So again, for continuity, the limit value equals the function value. So there's some problems that we do that are based around continuity. Generally, we'll throw in a piecewise function. If we look at the first example, we are determining if the function's continuous at x equals 3. So the first thing we need to do is establish whether the limit exists. So let's see. The limit as x approaches 3 from the left for f of x is going to equal, so if x is approaching 3 from the left, we're going to use the inequality where x is less than 3. So 3 plus 4 is 7. Next, we need to check the limit as x approaches 3 from the right. That means that we're going to use the inequality where x is greater than 3. So if we substitute in 3, we get, let's see, 3 squared is 9, minus 15 is -6, plus 3 is 7. Plus 13 is 7. So the left limit and the right limit are the same. So that means that the limit as x approaches 3 for f of x, that equals 7. That checks out. And so now we need to just know f of 3. Now f of 3, it says that if x is exactly equal to 3, that it should be 4. So our limit is not the same as our function value. So we would say f of x is not continuous at x equals 3 because the limit is not the same as the function value. Now, of course, it's easier to just write the limit as x approaches 3 of f of x is not equal to f of 3. Either one of those is sufficient. I would much prefer if you did this one. But in case you forget the words, this in the rectangular thing, Nebraska, maybe, Oklahoma, I don't know. It's the same thing. These two are equivalent. For the next example, we have an absolute value function. So we're trying to determine if the function is continuous at x equals -4. So we need to kind of do the same thing. First, we need to know the limit as x approaches -4 from the left for f of x. So that means if we're approaching -4, the x isn't -4. So that means we need to use the top thing. But what do we do for an absolute value function? So let's think about this. We're going to define, let me get my other notepad. We're going to have, we're going to put the absolute value of x plus 4 over x plus 4. Now, absolute value functions kind of imply their own piecewise functions. There are two cases. We can turn this into, let's see. Now, if x is less than -4, it means that x plus 4 is a negative value. So to do the absolute value, you do the opposite of a negative value. So the opposite of x plus 4 is negative x plus 4 over x plus 4. And that's going to be true if x is less than -4. And then we're going to have, say x is some value greater than -4 or -4 or greater, then the absolute value is going to be 0, or we don't need to change the sign. So we're just going to end up with x plus 4 over x plus 4 if x is greater than or equal to, actually just greater than a -4. The reason we did not put the equality is because we can't divide by 0. Now, this reduces. This is like having This is saying this function is actually -1 if x is less than -4, and that is +1 if x is greater than -4. So let's go all the way back then. So the limit as we approach 4 from the -4 from the left, well, we said that it's going to be -1 if x is some value less than -4. So if we're approaching -4 from the left, that means that this limit is -1, and the limit as x approaches -4 from the right is equal to, well, according to our thing we just wrote, is +1. So in this case, the function is not continuous at x equals 1 because the left limit and the right limit aren't equal, which means the limit doesn't exist. So we're going to say f of x is, we're going to introduce a new word, just discontinuous instead of not continuous, is discontinuous. How many u's do I have? I got enough. So f of x is discontinuous at x equals, -4. Because the limit as x approaches -4 does not exist. You might not be excited, so you could just put a period. But f of x is continuous at x equals -4 because the limit does not exist. That's it. This next example, we have to find the value of k so that f of x is continuous at x equals 2. All right, so going back over our definition of continuity, for this function to be continuous at x equals 2, it means that the limit for both of these things has to be the same thing with x is 2. So let's write that down. So I made some noise, I knocked some stuff over. So the limit must be the same for both, we're going to put in parentheses, not parentheses, quotation marks, for both branches of the piecewise function. So what that means is that when we substitute in 2 for this, it has to be the same thing as when we substitute in 2 down here. And that's just an equation, all right? So if we substitute in 2 for x, not k, if we substitute in 2 for x, this needs to be the same as that. By substituting in 2 for x, we get 4k minus 5. So we get 4k minus 5 must equal, if we substitute in 2, let's see, 4 plus 6 is 10, plus 5 is 15, plus k. So 4k minus 5 equals 15 plus k. Who knew in calculus we would get to solve an equation this simple? We get 3k equals 20 and k equals 20/3. Save your decimals, kids. We're just going to take this value of 20/3 and see if it actually works. So if k is 20/3, it means that this top thing is f of x equals, so 2 times 20/3 is going to be 40/3 x minus 5 if x is less than or equal to 2. And you know what? I forgot my little fancy brace. And then we're going to have x squared plus 3x plus 5 plus 20/3 if x is greater than 2. The smart thing to do is always check your work. So if we go back and substitute in 2, we're going to have 80/3 minus 5 on the top. So 80/3 minus 5, which is 80/3 minus 15/3, which is 65/3. And then for the second thing, if the second part of the piecewise function, if we substitute in 2, we get 4 plus 6 plus 10, 5 is 15. So 15 plus 20/3. So 15 plus 20/3. Well, 15 is the same as 45 thirds. And so 45 thirds plus 20 thirds is 65 thirds. So look, the values line up. That's how we know we did it correctly. So that's it. So again, what we did was, if we're finding this mysterious value of k, then the limits have to be the same thing. We will come across a similar problem when we start derivatives and finding values that make things differentiable. So the takeaway from this video is that for continuity, the limit value equals the function value. If you have questions, talk to me in class. See me before school. Thanks.